Out on the water, the deadline does not look like a spreadsheet. It looks like gray steel under a low sky, a working deck wet with spray, a crew moving with practiced economy around launch gear, consoles glowing in a dim command space, and small unmanned craft pushing away from the side of a larger ship into a restless sea. It looks like forklifts and container lifts on a pier. It looks like fuel, cables, antennas, control links, and watchstanders trying to turn new machines into something the fleet can actually trust. That is where the Navy's drone question now lives. For years, unmanned systems in naval service could be described as promising, experimental, or just over the horizon. They belonged to concept slides, test events, and future force discussions. They were important, but they were still easy to imagine as add-ons to the fleet that already existed. That framing is getting harder to sustain. In the spring of 2026, the Navy signaled something more serious. It announced that 7 companies had been selected for a Medium Unmanned Surface Vessel marketplace effort, with at-sea demonstrations ahead and a success incentive attached to performance. That is not the language of a distant idea. It is the language of a service trying to move from theory to selection, from promise to proof, and from prototypes to a force-structured decision that may shape how ships fight and survive in the years ahead. The pressure behind that decision is not difficult to understand. Modern naval operations stretch across enormous distances. Commanders want more sensing, more persistence, more reach, and more options than a smaller number of expensive crewed ships can provide by themselves. They also want to avoid wading through the longest and most expensive timelines in traditional shipbuilding every time a new operational need appears. The result is a search for mass, but not just mass in the old industrial sense. This is mass in the form of distributed systems, robotic systems, and platforms that can be risked in places where a manned ship carries far greater political, human, and operational cost. In practical terms, that means the Navy is no longer asking only whether unmanned vessels can function. It is asking whether they can be fielded in useful numbers, integrated into real formations, sustained over distance, and trusted enough to matter when the network is stressed and the sea is not calm. The imagery of that transition is already visible in official Navy releases. In one scene, unmanned systems are launched during a bilateral exercise with Norway, operating in a high north environment where mine countermeasures, maritime domain awareness, and the protection of undersea infrastructure are not abstract planning terms, but active mission areas. In another, the Navy formally establishes Unmanned Surface Vessel Squadron 7, making clear that robotic and autonomous systems are no longer being treated as occasional attachments to the fleet. They are becoming part of fleet organization. The squadron's mission language points directly at a future in which these systems must function in bandwidth-limited or denied environments, which is one of the most revealing details in this entire story. It suggests that the Navy is not designing these vessels only for ideal conditions or permissive demonstrations. It is trying to prepare them for operations in the kind of contested environment where every elegant concept is forced to prove itself. That distinction matters. It is one thing to operate a drone vessel in calm water with steady links, clean telemetry, and room for technicians to intervene. It is another to place unmanned systems into a crowded operational picture with weather, sea state, traffic, electromagnetic friction, and the ordinary confusion of naval movement. A drone boat is not useful to a fleet simply because it floats and answers a command. It becomes useful when it can contribute to a mission. While the deck is pitching, the operators are managing multiple tasks at once, and the command team needs a result rather than a demonstration. That is why the current moment feels less like a technology debut and more like a deadline. The fleet does not need another round of abstract belief. It needs evidence that unmanned systems can be incorporated into the routines and burdens of naval life. Launch and recovery, Maintenance and repair, payload handling, operational control, mission planning, logistics support, and the constant demand to keep systems available even after the cameras are gone and the weather turns ordinary again. The Navy's new marketplace approach for the Medium Unmanned Surface Vessel effort reflects that urgency. Instead of leaning entirely on the slow momentum of a traditional acquisition path, the service selected 7 companies for at-sea demonstrations and paired the effort with a success incentive. That structure tells its own story. It suggests a service trying to shift some risk outward, reward practical performance, and discover faster which designs can survive contact with real operations. The message is simple enough. Bring something that works at sea, not just something that reads well in a brief. This is an important change in tone because naval procurement has long been vulnerable to delay, overspecification, and the tendency to let perfect requirements consume usable momentum. The marketplace model does not remove that danger, but it is clearly an attempt to narrow the distance between concept and fleet use. Rather than betting on a single paper answer too early, the Navy is creating a competitive proving ground. The timeline itself adds pressure. Official Navy material pointed to an October 2026 test window for these at-sea demonstrations. That compresses the rhythm. Industry has to show hardware and performance. The Navy has to evaluate quickly enough for the effort to mean anything beyond another cycle of cautious optimism. Defense analysis reporting adds more texture to what that prototype phase may require. According to USNI reporting, prototype expectations have included range, measured in the thousands of nautical miles, speeds around 25 knots, operation in Sea State 4, and payload capacity measured in the tens of metric tons, with containerized payload concepts in view. Those details should be handled carefully, because they come through reporting rather than a formal public requirement release in the source set here. But even with that caution, the outline is unmistakable. The Navy is not searching for a toy. It is looking for a vessel large enough to matter operationally, fast enough to move with purpose, durable enough for imperfect water, and modular enough to carry changing mission packages. That last point may be one of the most consequential. Containerized payloads imply flexibility, but they also imply a logistics chain and an operating concept. Somewhere on a pier, that means crane movement, tie-down points, connector checks, power integration, payload swaps, and the quiet choreography of sailors and support personnel turning a hull into a mission asset. In visual terms, it is the motion of pallets, cases, forklifts, line handlers, and technicians in cranials and float coats working through checklists near the edge of the water. In operational terms, it is a test of whether unmanned systems can become manageable pieces of fleet routine rather than isolated engineering events. The Navy's wider exercise calendar gives this shift more meaning. RIMPAC 2026 is set to bring together 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. Even without claiming any specific unmanned role beyond what is sourced, the scale of that exercise matters. It reminds us that the U.S. Navy does not build for solo demonstration. It builds for coalition operations, for interoperability, for command structures that must absorb many platforms and many partners at once. Any unmanned vessel that hopes to matter in that future has to fit into that larger mosaic. It must be legible to commanders, usable by operators, and supportable inside the real pace of multinational naval activity. This is where the cold open becomes sharper. The Navy is not merely trying to buy a new class of vessel. It is making a larger bet about fleet architecture. Official announcements, fleet organization changes, and defense analysis reporting all point in the same direction. The service appears to be pushing toward a future in which unmanned systems help create a broader high-low mix, more numerous systems alongside more exquisite ones, more distributed presence alongside concentrated striking power, and more ways to complicate an adversary's picture without waiting decades for every answer to come in the shape of a traditional crude hull. Senior leadership framing, as reported in Defense Analysis earlier in 2026, described a future force built around risk-worthy mass and robotic autonomous systems rather than a one-size-fits-all fleet design. That phrase, risk-worthy mass, deserves to be heard slowly. It does not promise that unmanned vessels are cheap, simple, or disposable in the careless sense. It points instead to a strategic idea. A fleet needs enough distributed capability that it can absorb friction, take losses where necessary, keep sensing, keep moving, and keep imposing problems on an opponent. In that concept, unmanned systems are not present for novelty. They are present because numbers, distribution, and adaptability can create forms of resilience that a smaller set of highly valued ships cannot provide on their own. There is also an industrial argument running beneath all of this. Reporting on the 2026 shipbuilding debate connects unmanned systems to a wider discussion about modularity, a high-low fleet mix, and the bottlenecks facing the industrial base. That backdrop matters because the Navy's problem is not only strategic, it is also productive. Even when there is agreement about what the fleet should become, there remains the slower and less glamorous question of what can actually be built, integrated, and delivered on time. Unmanned systems are attractive in part because they appear to offer a way around some of the hardest constraints of traditional shipbuilding. But that promise will only hold if the systems can be manufactured, supported, upgraded, and fielded at scale without simply creating a new bottleneck under a different name. And scale is increasingly part of the language. Defense Analysis reporting in April said the Navy plans to deploy thousands of smaller unmanned surface vessels in the Indo-Pacific by 2030, alongside a growing number of medium unmanned surface vessels and integration with larger fleet formations. That reporting is not itself an official program commitment in the narrow sense, and it should be treated with that distinction in mind. Still, it captures the ambition surrounding this effort. The vision is no longer confined to a few demonstrations in sheltered contexts. It points toward a battle space seeded with more robotic presence, more distributed sensors and effectors, and more persistent maritime coverage spread across long distances. If that is the vision, then this is the moment when it has to start taking on the burdens of reality. Reality, in naval terms, is always physical. It is cable runs across a deck. It is corrosion starting where paint has been scraped thin. It is a control station operator staring at multiple feeds while a supervisor tracks the wider picture. It is a RHIB, or support craft, moving across choppy water nearby. It is a stern view of wake and gray horizon under a hard wind. It is a machinery space hum, a command room murmur, a plotted track, a launch checklist, and a recovery evolution carried out without spectacle. It is the logistics motion that follows every new promise: spare parts, software versions, maintenance intervals, training pipelines, and the unglamorous discipline of keeping systems ready for tomorrow after they were demonstrated today. That is why the drone deadline matters. Not because the idea of unmanned naval systems is suddenly new, but because the Navy now seems to be treating them as something that must move from possibility into structure. 7 companies have been selected. A test window is approaching. A squadron has been established. Operational exercises are already placing unmanned systems in visible mission sets. Leadership language has shifted toward mass, distribution, and robotic systems as part of the future fleet. Industrial arguments are being drawn around modularity and scale. The pieces are no longer scattered. They are beginning to align. The risk, of course, is that alignment in policy does not always become alignment at sea. The gap between those two worlds is where this story lives. In the months ahead, The Navy's drone future will be judged less by speeches than by launches, recoveries, endurance, payload integration, command and control performance, and whether these vessels can earn their place inside actual naval operations. That is the gamble now taking shape on the water. A fleet under pressure to expand its reach without waiting decades has chosen to press forward with robotic mass, medium unmanned vessels, and a procurement model designed to force practical results. The question is no longer whether unmanned systems belong in the conversation. The question is whether the Navy can turn them into a dependable part of the fleet before time, distance, and operational demand make the decision for it. The old fleet does not disappear when a new idea arrives. It keeps steaming, keeps refueling, keeps standing watch, and keeps carrying the weight of presence across long distances. On a gray morning at sea, that reality is easy to picture. A destroyer moves through a low swell with spray sweeping across the bow. On the weather deck, sailors in cranials and float coats work around lines, launch points, and containers with the quiet pace that comes from repetition. Inside, a command space glows with tracked symbols, voice circuits, and watchstanders leaning over consoles. The ocean is not interested in slogans. It tests everything the same way. It tests endurance, distance, timing, and whether a system can keep working when the sea rises and the network becomes uncertain. That is the setting in which the Navy's unmanned push has to prove itself. Not in a tidy slide deck, but alongside the inherited burden of the fleet already on station. The Navy is not starting from zero. It is trying to join new robotic and autonomous systems to an operating force that still depends on ships, crews, supply chains, and allied coordination spread across vast water. That is what makes this moment more serious than a technology demonstration. The challenge is not only to build unmanned craft, it is to make them useful inside the tempo and discipline of naval operations. Recent signals from the service show that the effort is moving beyond a purely experimental posture. In May 2026, the Navy announced that 7 companies had been selected for Medium Unmanned Surface Vessel Marketplace at sea demonstrations. That official announcement matters because it shows the service trying to accelerate learning with a different procurement rhythm. Instead of waiting for one traditional path to settle every answer before the water is touched, the Navy is using a marketplace approach tied to demonstrations and a success incentive. The same announcement described a $15 million success incentive and pointed to an October 2026 test window. In plain terms, the Navy is paying to find out what actually works at sea sooner, and it is shifting more of the early risk onto competing designs. That is a very different atmosphere from the older fleet model that shaped so much of naval power in the past. Traditional shipbuilding assumes long timelines, major capital commitments, and long service lives. The hulls are large, the crews are specialized, and every change carries consequences across maintenance, training, and industrial planning. The unmanned push does not replace that structure overnight. Instead, it presses against it. It asks whether part of the fleet's future mass can come from systems that are smaller, more modular, and less dependent on the full burden of a crewed warship. Seen from deck level, this is where the old fleet meets the new ocean. A replenishment evolution still has to happen. Fuel still has to move. Parts still have to arrive. Sailors still have to inspect gear, manage corrosion, stand engineering watches, and keep navigation exact in rough weather and crowded sea lanes. In that same world, unmanned systems are being asked to contribute to surveillance, mine countermeasures, maritime awareness, and other distributed tasks without demanding the same manpower footprint. The promise is not elegance. The promise is capacity. There are already signs of how the Navy wants to use that added capacity. During Arctic Century 2026, the Navy officially reported unmanned surface and undersea operations conducted with Norway. The stated mission areas included mine countermeasures, protection of undersea infrastructure, and maritime domain awareness. That setting is instructive. The High North is not a laboratory in the abstract. It is cold water, allied coordination, changing conditions, and the constant requirement to understand what is moving above and below the surface. A DVIDS-style visual sequence almost writes itself here. A steel deck glazed by northern light, crew members guiding equipment into position. A small unmanned craft lowered with careful hands, antennas wet with mist, and operators inside monitoring feeds while the sea state keeps everyone honest. The significance of that exercise is not just that unmanned systems were present, it is that they were used in an allied operational context where interoperability matters. The old fleet has always depended on allied habits of work, shared procedures, shared communications, discipline, shared confidence that a partner can carry part of the load. If unmanned systems are going to become part of the fleet rather than an attached experiment, they have to fit inside that same logic. They have to be launched, tracked, recovered, and understood within multinational operations. They have to be useful when conditions are imperfect. And they have to help commanders see more water without overloading the crews already responsible for the mission. That brings us to organization, which is often less glamorous than hardware, but usually more revealing. In April 2026, the Navy established Unmanned Surface Vessel Squadron 7. The official description tied the squadron to robotic autonomous systems and specifically to operations in bandwidth-limited or denied environments. That phrase is one of the clearest clues to what the Navy thinks the real operating problem will be. A robotic vessel is easy to describe when the connection is stable and the scenario is controlled. It is much harder to integrate when distance, congestion, disruption, or adversary action makes the network unreliable. The creation of a dedicated squadron suggests the Navy understands that unmanned systems are not just gadgets to be bought. They are systems to be organized, trained, and operated under pressure. Imagine the corresponding visual beat, a command room aboard a Pacific Fleet vessel or shore node, screens lit in subdued light, a watch team tracking multiple contacts, one operator focused on a remote craft, another coordinating routing, another managing the wider tactical picture. No futuristic fantasy is needed. The drama is procedural. The old fleet has always been a machine of routines executed under stress. The unmanned future will only matter if it can live inside those routines and still function when the easy assumptions break down. The scale of the wider naval environment reinforces the point. RIMPAC 22-6, according to the U.S. Pacific Fleet announcement, brings together 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. That is coalition scale. It means crowded planning tables, layered command relationships, and a maritime training environment big enough to expose coordination problems quickly. If unmanned systems are to become normal rather than novel, exercises of that size are where the fleet learns whether distributed systems can contribute to interoperability, missile proficiency, anti-submarine warfare support, or mine clearance operations without becoming a burden on the force that carries them. Defense analysis reporting adds another layer to the picture, though it should be treated as reporting rather than official certainty. USNI reported in April 2026 that the Navy plans to deploy thousands of smaller unmanned surface vessels to the Indo-Pacific by 2030, along with more than 30 medium unmanned surface vessels. If that reporting reflects the direction of travel, the implication is profound. The Navy is not merely testing a few robotic adjuncts. It is considering mass at a scale that would change how presence, sensing, and distributed operations are sustained across distance. The Indo-Pacific is the right place to understand the attraction. Range is relentless there. Time is long. Demand is constant. Every additional useful platform, even a smaller one, becomes part of the argument about how to stretch awareness and persistence across a theater too large for comfort. Another USNI report in May 2026 described prototype requirements for the Medium Unmanned Surface Vessel effort, including reporting around range, speed, sea state performance, payload, and containerized payload concepts. Reported figures included about 2,500 nautical miles, about 25 knots, operation in sea state 4, and a payload of roughly 25 metric tons. Those figures, again, should be understood as defense analysis reporting rather than official final specification. Even so, they help explain the Navy's interest. The vision is not of a toy craft hugging the pier. It is of a vessel with enough reach and useful carrying capacity to matter, and modular enough to take on different payload roles. Containerization is important here because it speaks the language of logistics as much as technology. The old fleet understands modules, load plans, support requirements, and the value of swapping purpose without redesigning an entire ship. This is where the industrial question enters the frame. Defense analysis coverage of the Navy's 2026 shipbuilding debate linked unmanned systems to a broader high-low fleet idea and to a modular industrial strategy constrained by bottlenecks. That context matters because no naval transformation happens only on the water. It also happens in yards, in supply chains, in contract structures, and in the ability to build enough of the right thing on time. The old fleet was shaped by an industrial age that rewarded size, concentration, and long lead times. The new ocean, at least in the Navy's current thinking, may require a mix, some large, exquisite platforms, and a wider layer of more numerous systems that can create what senior leadership has described as risk-worthy mass. That leadership framing is important. In February 2026, Defense Analysis Reporting described senior Navy leadership arguing against a one-size-fits-all future fleet and instead describing a hedge force built around robotic autonomous systems and risk-worthy mass. Even at the level of language, this is a break from older assumptions. It suggests that part of the fleet is being imagined not as a mirror image of the traditional ship, but as a complement to it, more distributed, more numerous, and more acceptable to place in riskier situations than a major crewed combatant. Still, none of this removes the burden of proof. The ocean remains the final editor. On a wet deck, equipment still has to start. Launch and recovery still have to be safe. In a command space, data still has to arrive in time to matter. In the logistics chain, movement still has to be coordinated from pier to ship to sea and back again. The old fleet meets the new ocean at those points of friction. Not in promises, but in procedures. Not in marketing language, but in whether crews can actually fold unmanned systems into the rhythm of operations. So, Chapter 2's real picture is not a clean handoff from old to new. It is an overlap. Gray hulls and remote craft, human watch teams and robotic systems, allied exercises and prototype competitions, industrial bottlenecks and urgent operational distance. The Navy's gamble is that unmanned systems can become a dependable layer of fleet architecture before strategic demand outruns the traditional pace of adaptation. The old fleet is still here, carrying the load. The new ocean is asking for more coverage, more endurance, and more distributed presence. Between them, the Navy is trying to build a force that can do both. A fleet does not hedge its future by replacing everything at once. It hedges by adding layers. It keeps the ships that already carry presence across the ocean, and at the same time, it begins building a second kind of force around them. In Navy planning, that emerging layer has been described as a hedge force, a formation built less around a single perfect ship type and more around risk-worthy mass, robotic autonomous systems, and a wider spread of capability across the water. The idea is not to erase the traditional fleet. The idea is to give that fleet more reach, more persistence, and more options in seas that are getting harder to watch in full. On paper, that can sound abstract. At sea, it looks more concrete. A camera mounted high on a destroyer bridge looks down over a weather-dark deck. safety lines taut in the wind, sailors moving between equipment stations in heavy float coats as spray lifts off the bow. Farther aft, a work area is cleared, tie-down points exposed, cranials and gloves bright against the gray, non-skid. The scene is familiar: crew, steel, salt, routine. The hedge force begins here, not in a laboratory apart from the fleet, but inside the fleet's daily habits of launch, recovery, command, refueling, maintenance, and watchstanding. That matters because the Navy is not pursuing unmanned systems as a separate curiosity. It is organizing for them. In April 2026, the service established Unmanned Surface Vessel Squadron 7, or USVRON 7, with a mission centered on robotic autonomous systems and operations in bandwidth-limited or denied environments. That detail is easy to miss, but it goes to the center of the concept. A robotic vessel is only useful if it can function in the kind of conditions navies actually worry about, where links are interrupted, access is contested, and operators cannot assume an uninterrupted stream of commands. The hedge force is being framed for that harder environment, not for a perfectly connected demonstration range. In practical terms, that means the Navy is trying to build a structure that can stretch outward from the manned fleet without snapping its control relationships. Picture a command room lit in low red and blue, watchstanders seated before repeating tactical displays, one console tracking surface motion, another monitoring air contacts, another following a detached unmanned system operating farther from the formation. Nobody in that room is supposed to be performing magic. The attraction of the hedge force is not mystery, it is distribution. More nodes, more sensing, more decoys, more relay points, more specialized craft, and more ways to occupy space that would otherwise remain thinly covered. That logic becomes easier to see when the scale of current operations comes into view. RIMPA T 2026, the 30th edition of the exercise, is set to bring together 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. Those numbers describe coalition power, but they also hint at the size of the maritime problem itself. A modern fleet exercise is a moving web of ships, aircraft, logistics flows, communications paths, and national command relationships spread across immense water. Even a large manned fleet can feel sparse in an ocean context. The hedge force concept grows out of that pressure. It asks how a Navy can generate more distributed presence and more operational texture without waiting only on the long timelines of traditional shipbuilding. So the new idea is not simply more robots. It is a high-low mix inside the future fleet. Reporting on the 2026 shipbuilding debate has tied unmanned systems to a broader architecture that runs from the seabed to space and leans on modular, distributed approaches rather than a single, concentrated answer. In that framing, the hedge force is not a separate fleet beside the fleet. It is one part of a broader maritime structure, meant to complement larger ships, fill gaps, and create additional mass where cost, time, and industrial bottlenecks make it difficult to build only upward. There is also a harder strategic undertone beneath the language of innovation. A hedge exists because the future is uncertain. Naval planners can see pressure from range, from geography, from logistics, from industrial limits, and from the simple fact that no Navy can be everywhere with exquisite manned platforms alone. The answer under discussion is to create more numerous systems that can extend scouting, support specific missions, and complicate an opponent's picture. When senior leadership talks about risk-worthy mass, the phrase suggests a force that can be employed in larger numbers and with different cost assumptions than the most precious capital assets in the inventory. At sea, that still comes back to handling gear and moving weight. A useful visual beat for this chapter is not a futuristic animation, but a working deck scene, a crane swinging over a mission area, a pallet jack inching a containerized module into place, sailors guiding motion by hand signal, while the sea state keeps everyone braced and deliberate. One of the notable threads in current reporting on medium unmanned surface vessels is the emphasis on payload and containerized flexibility. Defense reporting in May described prototype MUSV expectations in terms of substantial range, speed, and payload, with room for containerized mission packages. Even when treated carefully as reporting rather than final official promise, the implication is clear enough. The Navy is interested in adaptable platforms, not just one narrowly fixed machine. That flexibility is part of why the procurement method matters so much. In late May, the Navy announced 7 companies selected for a MUSV marketplace effort built around at-sea demonstrations, with a test window set for October 2026 and a success incentive attached to performance. That is an important clue to the hedge force mindset. Instead of treating unmanned surface vessels purely as a distant, highly polished acquisition program, the service is testing a marketplace approach that puts multiple competitors into practical evaluation and rewards demonstrated success. The pace is still military pace. Nothing here suggests instant transformation, but it does suggest a willingness to search for working designs by trial at sea rather than by waiting for a single immaculate answer to emerge from a longer traditional path. On a pier or flight deck, the significance of that choice would not announce itself in slogans. It would show up in the variety of hull forms, launch methods, support equipment, and maintenance routines surrounding the effort. Different craft, different crews, different technical representatives, different checklists clipped to boards in the wind. In the logistics motion around the event, the hedge force reveals its real complexity. Systems have to be fueled, repaired, updated, observed, recovered, and understood by sailors who still have a ship to run. The future fleet will not be decided only by whether an unmanned vessel can move through the water. It will be decided by whether it can fit into the Navy's durable machinery of operations. That is one reason exercises with allies matter. During Arctic Century 2026, the Navy announced unmanned surface and undersea operations alongside Norway in missions tied to mine countermeasures, maritime domain awareness, and the protection of undersea infrastructure. This was not presented as science fiction. It was presented as operational use in a bilateral context in northern waters where environment and distance sharpen every demand. A cold sea state, low light, disciplined launches, safe recovery procedures, crews working in layers and helmets around compact craft and support gear. These are exactly the kinds of scenes that make the hedge force legible. The point is not only that unmanned systems exist. The point is that they are being folded into real mission sets that matter to allies and to maritime security. The same pattern appears in the Navy's broader discussion of the Indo-Pacific. Defense reporting this spring described plans pointing toward thousands of smaller unmanned surface vessels in that theater by 2030, alongside a force of medium unmanned surface vessels and integration with carrier strike groups. Because that reporting is not itself a formal program of record statement, it has to be handled with care. Still, as a directional indicator, it shows the scale of the wager. The hedge force is not imagined as a boutique add-on. It is being discussed in terms of quantity, spread, and operational integration across long range. And range is the key word. Oceans punish short-legged ideas. Any fleet architecture that aims to matter in the Indo-Pacific has to respect distance, not as a background condition, but as the defining fact. That is why the Navy's interest in endurance and payload for medium unmanned vessels matters. It is why distributed systems matter. It is why bandwidth-denied operations matter. A force meant to hedge against future conflict or strain cannot depend on being close, comfortable, and continuously connected. It has to function out in the weather, across transit lanes, with support stretched and time extended. Imagine the visual rhythm here. Dawn on a replenishment ship, hoses and lines moving under tension, forklifts shuttling stores. A command information center on another hull tracking contacts while a detached unmanned craft feeds back limited but useful awareness. Then a cut to an engineering compartment where sailors check ordinary machinery, followed by a stern camera framing a smaller vessel working astern in moderate seas. Nothing sensational, just the Navy's basic truth: endurance comes from systems that can be sustained. The hedge force only becomes real if it can live inside that ordinary grind. That is why industrial base questions stay close to the center of this story. The 2026 shipbuilding debate has linked unmanned systems to a broader modular and distributed industrial strategy while also acknowledging bottlenecks. This is the sober side of the hedge. A Navy can describe a future force in compelling terms, but it still has to source parts, build hulls, fit payloads, train crews, manage suppliers, and maintain tempo over years. The marketplace approach for MUSV prototypes suggests an attempt to widen the path forward by bringing more firms into contention and letting the sea help sort theory from utility. In that sense, the hedge force is both an operational idea and an industrial one. It asks whether naval mass can be generated by a mix of methods instead of by a single pipeline. It asks whether useful capability can be distributed across many systems instead of concentrated only in a few large ones. And it asks whether the Navy can gain time by experimenting in parallel, learning faster at sea, and accepting that not every useful vessel in the future fleet needs to resemble the old hierarchy of warship categories. Still, the old fleet remains the frame around all of this. The destroyer on station, the replenishment ship on schedule, the submarine in exercise, the aircraft overhead, the multinational formation at RIMPAC, the sailors at consoles and on deck, they are the structure into which the hedge force must fit. The gamble is not that robots will replace seamanship. The gamble is that a manned fleet, already stretched by geography and mission load, can be strengthened by a larger, more distributed layer of autonomous and semi-autonomous systems built for persistence, experimentation, and scale. So Chapter 3 ends not with a futuristic certainty, but with a practical image: a gray sea. A ship holding steady enough for work. Sailors guiding equipment across the deck with careful hand signals. A small, unmanned craft secured, checked, and sent back out into open water. Inside the command room, another watch begins. The hedge force is not a clean break from the fleet that exists. It is a wager placed from inside that fleet's daily labor. More coverage, more reach, more distributed presence. Not a perfect answer, but a deliberate second layer, built while the old fleet keeps steaming. The wager begins far from any ceremonial launch. It begins in the work of the fleet, in the slow rhythm of lines under tension, boots crossing a wet deck, cargo handlers guiding pallets into place, and watch teams studying a broad sea that never stops changing. From that daily labor, the Navy is shaping a new bet. Not a bet on replacing every gray hull that already carries presence across the ocean, but a bet on adding another layer beside it. A layer built around unmanned systems, medium unmanned surface vessels, and a procurement model meant to move faster than the old path usually allows. That is what makes this moment different. The idea is not only about the craft themselves, it is about how the Navy is trying to buy them, test them, and pull them into real fleet use before the long machinery of traditional shipbuilding closes around every decision. In May 2026, the Navy announced that 7 companies had been selected for Medium Unmanned Surface Vessel Marketplace at-sea demonstrations. The demonstrations were tied to a competitive structure, with a success incentive of $15 million and an at-sea test window set for October 2026. That combination matters. It signals that the Navy is not only asking industry to submit designs on paper, it is asking for performance in the water. On screen, this is where the imagery should stay grounded. A workboat wake rolling under a low steel horizon, spray lifting off a bow in moderate chop. Sailors at a control station, hands on throttles and touchscreens, while another crew member tracks range and bearing on a display. A logistics detachment cinching straps over a containerized load. A crane hook settling slowly into position above a weathered deck. The camera does not need secrecy or spectacle, it needs process. The marketplace bet is a story about process becoming strategy. For years, unmanned systems often lived in the public mind as demonstrations, side projects, or promising tests that might never become routine fleet hardware. This new approach suggests the Navy wants something more practical. A prototype phase, at-sea demonstrations, success incentives, a structure that pushes risk outward, away from waiting until a fully mature program settles into a long and familiar acquisition cycle. The intention is not to remove risk. The intention is to expose it earlier, where performance at sea can prove what brochures cannot. That approach fits the wider language now surrounding the future fleet. Senior Navy leadership has described a hedge force, a force built around robotic autonomous systems and what has been called risk-worthy mass, rather than a one-size-fits-all fleet design. The concept is clear even when the language is careful. The Navy does not expect one class of ship to solve every operational problem. It expects to keep its traditional force and add a second layer of more distributed systems around it. Smaller systems, different systems. Systems that can widen coverage, extend presence, and complicate an opponent's picture of the battle space. The camera can support that argument with ordinary naval motion. A destroyer bridge wing at dusk, wind flattening a lookout's jacket against the rail. Below, a small boat detachment checks fuel lines and protective covers. In a command room, screens glow in low light, while watchstanders pass updates across headsets. Somewhere else, on another deck, a compact unmanned craft sits lashed down beside conventional gear, neither futuristic nor theatrical, just another tool awaiting tasking. That is the important visual truth. The fleet is not stepping into an entirely separate future, it is absorbing a new layer into the old one. Recent operations help explain why the Navy wants that layer. During Arctic Sentry 2026, the United States and Norway launched unmanned systems in a bilateral exercise tied to mine countermeasures, maritime domain awareness, and the protection of undersea infrastructure. Those are not abstract missions. They point to cold water, difficult navigation, alliance coordination, and a battle space where unmanned systems can do useful work without replacing the manned ships and crews that still anchor the operation. The lesson is not that robots take over. The lesson is that distributed tools can extend the reach of a coalition force in difficult environments. The visual beat here should be practical and northern. Gray sea state, icy spray or low cloud over open water. A launch sequence from the side of a support vessel. Crew in cold weather gear moving carefully along a damp deck. A small craft clearing the ship and settling into the swell. Cut then to a command console where operators track position data and sensor feeds while speaking in measured tones. This is the living texture of the hedge. Human crews, allied coordination, and unmanned systems sharing the same mission space. The Navy has also moved to formalize the organizations that will make such operations routine. In April 2026, Unmanned Surface Vessel Squadron 7 was established with a mission centered on robotic autonomous systems and operations in bandwidth, limited or denied environments. That detail is essential. It suggests the Navy is not imagining an unmanned future built on perfect connectivity and uninterrupted control. It is preparing for the harsher reality in which networks degrade, links fail, and units still need to function. The marketplace bet, therefore, is not only about buying hulls. It is about building doctrine, command habits, and crew familiarity around systems that must survive imperfect conditions. That is where the chapter's title begins to show its full meaning. A marketplace suggests variety, competition, and adaptation. The Navy appears to want those qualities because the strategic problem itself has become too broad for one narrow answer. According to Defense Analysis reporting in 2026, the Navy's unmanned planning included not only medium vessels, but also the prospect of deploying thousands of smaller unmanned surface vessels in the Indo-Pacific by 2030. Reporting from the same period also described prototype MUSV requirements in the range of about 25 knots, roughly 2,500 nautical miles, sea state for performance, and a payload near 25 metric tons with containerized payload options in view. Those details are less important as promises than as indicators of intent. The Navy is trying to define useful, repeatable capability rather than chase a single exquisite prototype. The footage here can become busier without becoming dramatic. Forklifts crossing a pier, modular equipment secured in container frames, a ship's deck team guiding movement with hand signals, a replenishment station rigged and ready. On a plotting screen, icons spread across a patch of digital ocean, some manned, some unmanned, all part of the same picture. In the background, the sea remains moderate, the light overcast, the working tone controlled. The chapter is not about a revolutionary machine arriving from nowhere. It is about logistics learning to carry a new category of presence. That same logic appears at the scale of exercises. RIMPET 2026 was announced as the 30th iteration of the exercise, bringing together 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. Those numbers matter because they show the size of the coalition framework into which unmanned systems must fit. Any marketplace solution that hopes to matter to the future fleet must live inside real naval complexity, combined operations, crowded sea space, missile proficiency events, anti-submarine warfare, mine clearance, and the ordinary friction of multinational coordination. An unmanned vessel that works only in isolation is not yet a fleet tool. A useful unmanned vessel must operate in the weather, tempo, and organizational density of an exercise like that. So the bet is both industrial and operational. On the industrial side, the 2026 shipbuilding debate linked unmanned systems to a broader high-low mix and a modular distributed approach to production, even while acknowledging industrial-based bottlenecks. On the operational side, the fleet is already organizing squadrons, running allied exercises, and preparing demonstration windows that push new systems toward real use. One side without the other would be incomplete. Buying novel craft without a place for them in fleet practice would leave them stranded. Building concepts without an acquisition path would leave them trapped in briefing slides. This is why the marketplace approach carries such weight. It accepts that the old fleet must keep steaming. Carrier groups, destroyers, submarines, logistics ships, and the crews who sustain them are not pausing while a future force is invented. The hedge has to be built from inside active service, from maintenance periods, from test ranges, from commands willing to absorb new systems while still meeting current tasking. That makes the wager more credible and also more difficult. Every unmanned layer must justify itself, not in theory, but in time saved, space covered, and options created for commanders already burdened with today's demands. The right closing visuals are simple. A wide shot of a ship cutting through a calm but restless sea at first light. On deck, sailors move with the efficiency of repetition, checking lashings, consulting clipboards, watching the horizon. In a nearby control space, operators sit before their consoles, speaking softly as data updates across the screen. A smaller unmanned craft rides within the larger pattern of the task group, not replacing the fleet, not overshadowing it, but extending it. This is the marketplace bet in its clearest form. More than a procurement experiment, More than a technology trial, it is an attempt to buy time, reach, and distributed presence without waiting for a perfect answer. And perhaps that is the deepest logic behind it. A fleet that faces growing demand across wide oceans cannot wait for certainty before it starts layering new tools into service. It experiments, organizes, tests, and buys in parallel. It places a wager from within its own daily labor. Not that every prototype will succeed, not that every promised concept will endure, but that a second layer, built now, might give the fleet more resilience than delay ever could. In that sense, the marketplace is not a side story to naval power. It is becoming one of the ways naval power tries to adapt before the pace of events leaves it behind. What matters now is not the announcement, but the assignment. Once these unmanned boats leave a pier, they stop being an abstract procurement idea and become part of the oldest problem in naval warfare, doing useful work at sea, on time, in weather, alongside other ships without creating more burden than they remove. That is the real test behind the Navy's current wager. A medium unmanned surface vessel cannot justify itself by merely existing or by completing a carefully staged demonstration in calm water. It has to fit into the daily labor of the fleet. It has to move with other units, hold station when the sea is unsettled, carry equipment that matters, and remain useful when communications are weak, delayed, or denied. The promise is not automation for its own sake. The promise is practical naval work delivered at useful scale. In public descriptions of the current prototype effort, the requirement is already framed in those practical terms. Defense reporting on the selected designs described a vessel expected to cover significant distance, maintain meaningful speed, carry a substantial payload, and support containerized mission equipment. Even in summary form, that tells us something important. These boats are not being imagined as drifting sensors with decorative autonomy. They are being shaped as working hulls. They are expected to move, endure, carry, and adapt. That shifts the picture immediately. In visual terms, this is not science fiction. The footage language is recognizably naval. A gray hull working through a moderate sea, spray crossing the bow, antennas above a compact superstructure, a deck arrangement designed not for ceremony, but for access, fastening points, mission modules, maintenance space, and safe movement by the crew or detachment that tends the vessel before launch, after recovery, or during pierside preparation. A camera angle from the quarter with swells lifting the stern. Another from the deck edge showing tie-downs, fittings, housings, and the disciplined blankness of equipment made to survive salt, motion, and repetition. The first task these boats must do is simply stay useful while underway. That sounds obvious, but it is not a trivial requirement. A naval platform earns trust only when it performs in real sea conditions, under real fleet schedules, with the ordinary friction of saltwater operations. It must keep its course, protect its onboard systems, preserve its payload, and continue doing its job after the novelty has worn off. It must be ready not just for the launch photo, but for the 5th day, the 10th transit, the second fault, the rougher weather, and the midnight check, when someone in a control station wants to know if the vessel is still where it should be. That is why the requirement for sea handling matters as much as any software discussion. A vessel operating in open water will meet changing sea state, spray, rolling motion, and the constant punishment of corrosion and vibration. Every sensor mount, hatch, cable run, and container interface must survive that environment. In a briefing room, this translates into quiet but critical questions. Can the boat hold a stable mission profile while the water is moving under it? Can its systems remain available after repeated shock and exposure? Can its mission package stay secure and functional? Can sailors sustain it with the tools and routines the fleet already understands? The second task is carrying useful mission weight. The public discussion around this program points repeatedly toward payload, and that is where the fleet value either grows or collapses. A medium unmanned vessel is not important because it is unmanned. It is important only if it can take something meaningful to sea, sensing gear, communications packages, modular mission equipment, or other containerized capability that extends the reach of a larger force. That point deserves emphasis. Naval power has always depended on what a hull can bring forward and keep in action. In the unmanned case, the logic remains the same. A vessel without useful payload is little more than a demonstration platform. A vessel with modular payload becomes something else, a flexible node in a wider formation. It can be assigned to watch, relay, screen, support, or contribute to a mission package without demanding the same crew footprint as a traditional ship. This is where the imagery becomes especially concrete. Think of the loading phase. Pallets moving across a logistics apron. A crane or handling gear placing a mission module where it must sit. Sailors and technicians checking fasteners, connectors, housings, seals, and clearances. A close view of gloved hands securing fittings. A deck marked for safe movement and equipment placement. A final walk-around before the vessel is released to its next step. None of this is glamorous, but all of it is naval truth. The future force will depend on such motions as much as on any briefing slide about autonomy. The third task is operating as part of a larger formation rather than as a lone experiment. Official Navy statements about new unmanned organization already point toward distributed systems and operations in bandwidth, limited or denied environments. That language matters because it strips away an easy illusion. These vessels are not being built for a perfect network. They are being prepared for a fleet fight in which communication may be incomplete, delayed, contested, or lost. So the boat must do more than receive constant instruction. It has to continue functioning when the flow of control is less tidy than a lab demonstration. It has to support a concept of operations in which human commanders set the task, define boundaries, and integrate the vessel into a broader plan, while the vessel carries out enough of its behavior reliably to remain worth deploying. The exact technical means may not be public in detail, and there is no need to pretend otherwise. But the operational requirement is plain. If the vessel becomes helpless the moment connectivity degrades, then it is not a resilient fleet asset. It is a fragile accessory. That requirement also changes what the control picture looks like. The decisive scene is not a fantasy command chair. It is a watch floor. Consoles lit in low light. Operators seated at control stations. A tactical screen with multiple tracks, a supervisor leaning over a shoulder, a voice circuit passing short confirmations, a coffee cup near a keyboard, a hand marking a note on a watch log. The unmanned vessel must fit into that room. It must give the operators enough confidence and clarity that they can incorporate it into real decisions rather than isolate it as a novelty. The fourth task is supporting surveillance and awareness across wider water. Official Navy reporting from Arctic Sentry 2026 described unmanned operations tied to maritime domain awareness, mine countermeasures, and the protection of undersea infrastructure in cooperation with Norway. That matters because it shows the type of work the Navy already associates with these systems, not theatrical independence, but practical contribution to the maritime picture. A medium, unmanned surface vessel does not need to do everything. It needs to be able to take part in the gathering, relaying, and persistence that naval operations require. In a northern exercise setting, that may mean moving through cold water under a low sky, with crewed ships, aircraft, and other unmanned systems, all contributing to a shared understanding of what is in the operating area. In a different theater, the specific geometry changes, but the principle does not. The vessel earns its place by helping commanders see farther, stay present longer, or distribute tasks more efficiently across the force. The fifth task is working inside coalition and exercise environments that are already crowded, disciplined, and demanding. RIMPT 2026, by official Navy figures, brings together 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. In such an environment, an unmanned vessel cannot be a self-contained curiosity. It must be safe to integrate, understandable to command relationships, and useful within the broader exercise logic of interoperability, missile proficiency, anti-submarine warfare, and mine clearance. That tells us something critical about the threshold for success. A boat that only performs well in a sterile test lane is not enough. The Navy needs something that can exist inside the pressure of real multinational operations, where ships maneuver, aircraft sortie, sea states change, and command structures must remain coherent. In footage terms, that means the unmanned platform framed not by empty horizon alone, but by company, a larger ship on the beam, aircraft overhead, a formation at distance, a RHIB crossing nearby, signal lights at dusk, wake lines intersecting beneath a pale sky. The vessel must belong inside that visual world. The sixth task is contributing to a broader fleet architecture, not merely to one niche mission. Public defense analysis has tied the unmanned push to a wider high-low mix and to a more modular industrial strategy. Senior leadership language around robotic autonomous systems and risk-worthy mass points in the same direction. The underlying logic is clear, even if every future number remains contested. The Navy is looking for ways to generate more presence, more options, and more resilience without waiting for every answer to arrive through slow traditional shipbuilding alone. That is why these boats must do ordinary fleet work extraordinarily well. They must be movable, maintainable, and adaptable enough to be bought in meaningful quantity and used in different roles, without each new mission becoming a bespoke program. If they require exquisite handling, exotic support, or endless exceptions, then the promise of scale begins to dissolve. If, however, they can be produced, fitted with modular payloads, integrated into commands, and sent out to do useful jobs repeatedly, then the Navy's wager starts to look more like architecture than experiment. And that returns us to the deck, because strategy eventually cashes out there. A sailor checking a tie-down. A technician examining a connector housing. An operator watching a track stay steady on the screen. A support team moving gear through a pier-side staging area. The vessel rising and falling in a working sea, not as a symbol, but as a task-bearing machine. That is what these boats must actually do. They must translate procurement theory into seaworthy routine, autonomy into dependable contribution, and fleet ambition into repeatable action. If they can manage that, then the Navy's robot fleet gamble begins to look less like a headline and more like a new layer of naval labor taking shape in plain sight. The farther north this story moves, the less it resembles a tidy technology presentation, and the more it starts to look like old naval work in a hard place. Cold water, distance, weather, uncertain communications, and the constant question of what is happening below the surface all force every new idea to prove itself. In that environment, unmanned systems are not interesting because they are modern. They are interesting only if they can carry part of the burden that sailors and ships have always carried, searching wide areas, watching long approaches, checking dangerous waters, and helping commanders build a usable picture of the sea. That is why Arctic Sentry matters. In May 2026, the Navy described unmanned systems operating during Arctic Sentry 2026, with Norway in a mission set that included mine countermeasures, maritime domain awareness, and the protection of undersea infrastructure. Those are not decorative tasks. They sit close to the center of what makes northern waters strategically difficult. The Arctic and the broader high north are defined by long distances, harsh conditions, and a battle space where the important question is often not what is visible on the horizon, but what is moving, resting, or hidden below it. In footage terms, this chapter lives in practical images. A gray ship in cold light, hull wet with spray, moving through a restless sea. Sailors in heavy gear on an open deck, checking tie-downs, watching lines, guiding equipment with careful hand signals. A launch point cleared and ready. A small unmanned craft eased into the water. A crew station inside, screens glowing in a dim control room. Operators seated shoulder to shoulder, headsets on, hands moving between keyboard, display, and radio circuit. None of it needs to look theatrical. In fact, it should not. The point is disciplined routine under difficult conditions. The undersea problem has always punished vagueness. A navy can speak in broad terms about presence and deterrence, but beneath the surface the work becomes specific very quickly. Mines have to be found. Approaches have to be checked. Cables, seabed systems, and critical undersea infrastructure have to be monitored and understood. Maritime domain awareness has to extend beyond what a watch team can see from a bridge wing. And because these waters are shared with allies, the picture has to be built in a form that partners can use together. That is where the Arctic Sentry activity begins to connect directly to the larger unmanned fleet story. The official description of the exercise is careful, and it should be. It does not promise magic. It does not claim that unmanned systems have solved the Arctic. What it shows is something more important: the Navy and Norway using unmanned surface and undersea systems in a bilateral setting for real mission categories that matter in northern waters. That turns the discussion away from abstract future concepts and toward integration. Can unmanned systems contribute to a combined maritime picture? Can they support mine countermeasures? Can they help watch sensitive undersea areas? Can they do it in conditions where range, cold, and communications friction are not theoretical inconveniences, but daily facts? That last point is crucial. New machines are easy to admire at the pier. The real test begins once they leave the pier and become subject to sea state, handling constraints, launch and recovery procedures, maintenance rhythms, and the ordinary fatigue of operations. Even when the equipment works, naval usefulness depends on whether a crew can incorporate it into the flow of a mission. Deck crews have to move safely. Operators have to manage the control burden. Commanders have to decide what information matters and what is only noise. Logistics teams have to keep batteries, fuel, connectors, spares, and handling gear moving on time and in the right order. A robotic vessel may be unmanned at the edge, but it still arrives wrapped in very human labor. That is part of the deeper significance of the Navy's current unmanned push. Senior leadership has described a future hedge force built around robotic autonomous systems and what has been framed as risk-worthy mass rather than a one-size-fits-all fleet design. In plain language, that means the Navy is trying to build layers into the fleet. Not every mission needs the same kind of ship. Not every task should consume the same kind of scarce manned platform. Some jobs call for endurance and presence. Some call for scouting, sensing, or carrying a modular payload. Some call for a system that can be sent into harder spaces without placing a large manned crew at the same level of direct exposure. The Arctic puts pressure on that logic in a useful way. If a concept survives there, it is cleared more than a laboratory benchmark. The High North is a setting where communications can be strained, sea conditions can be punishing, and the operational picture can be incomplete for long stretches. That gives special relevance to the creation of Unmanned Surface Vessel Squadron 7 in April 2026. The Navy said the squadron was established to operate robotic autonomous systems in bandwidth, limited, or denied environments. That phrase deserves attention because it quietly rejects a comforting fantasy. The future unmanned fleet cannot depend on perfect connectivity. It has to operate in conditions where links degrade, where control is not constant, and where autonomy, procedure, and operator discipline have to bridge the gap. This is where the surface story meets the undersea story. A medium unmanned surface vessel may be discussed in terms of speed, range, payload, or containerized mission packages. But in places like the Arctic, the The real question is how such systems contribute to the search problem. A force commander wants a wider picture without exhausting high-end ships on every line of effort. A maritime staff wants more sensors, more persistence, and more options for dangerous or repetitive tasks. A mine warfare team wants more reach in water that has to be checked carefully. An allied formation wants interoperability that works beyond the briefing slide. Arctic Sentry gives a glimpse of that logic in motion. The images that fit this section are not secretive or sensational. They are procedural. A cold crane swing over the deck, a rigid inflatable nearby as safety boat cover, non-skid shining with spray, sailors securing gear against the ship's motion, a compact unmanned craft bobbing just off the stern. In the operations room, a watch officer leaning toward a display as tracks populate the screen, a plotting surface marked with routes and operating areas, a technician tracing a cable path with a gloved hand before a final connection check, a galley coffee urn strapped for sea, a passageway with personnel moving around cases and equipment. Logistics motion matters because this is what turns a concept into sustained work. The wider naval calendar reinforces the point. RIMPAC 2026 was announced as bringing together 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft, with exercise areas including anti-submarine warfare and mine clearance. That coalition scale matters because the unmanned future is not being imagined for a vacuum. It is being shaped for fleets that have to work with allies across vast distances in mixed mission sets. If unmanned systems are going to become a meaningful layer of naval labor, they have to fit into multinational exercises, shared procedures, and command relationships that are already demanding before a single drone enters the picture. Outside official statements, defense reporting has described an even broader ambition: thousands of smaller unmanned surface vessels in the Indo-Pacific by 2030, more than 30 medium unmanned surface vessels by the same general period, and prototype requirements discussed in terms of substantial range, useful speed, and meaningful payload capacity. Whether every part of that ambition arrives on time is less important here than what the reporting reveals about direction. The Navy is not talking about a boutique demonstration force. It is talking about scale, distribution, and practical contribution to fleet operations. And yet the Arctic reminds us that numbers alone are not an answer. A robot fleet that cannot handle rough water, limited bandwidth, alliance coordination, or the undersea search problem is only mass on paper. The harder achievement is operational trust. A commander has to believe the system will arrive, endure, report clearly, and integrate cleanly. A deck team has to trust launch and recovery procedures. An operator has to trust what the system is telling them. An allied partner has to trust that the contribution is useful rather than distracting. Trust, in naval terms, is usually built from repeated competent performance, not from slogans. So Chapter 6 is where the gamble acquires its northern edge. Arctic Sentry shows unmanned systems entering a mission space defined by mines, infrastructure protection, maritime awareness, and allied coordination. USV Arrow N7 shows the Navy organizing itself for robotic operations in conditions where communication may be constrained. The broader fleet vision points toward distributed systems and layered mass. But the undersea problem remains the stern examiner of all these ambitions. Beneath the surface, the sea still demands patience, accuracy, and reliable contribution. If the Navy's unmanned force can meet that standard, then these machines stop being futuristic extras and start becoming what every fleet ultimately needs from new tools, another dependable way to do difficult work at sea. What matters now is not whether the Navy can demonstrate an unmanned vessel in a controlled event. What matters is whether it can build a hybrid fleet quickly enough for the kind of ocean problems it says it expects to face. That is a different test. A demonstration can prove that a machine moves, senses, launches, recovers, or stays on station. A fleet has to do more. A fleet has to absorb weather, distance, maintenance, communications gaps, supply delays, training burdens, and the plain friction of operating at sea day after day. That is why the current American push toward unmanned naval mass is so consequential. It is not simply a technology story. It is a shipbuilding story, a logistics story, an operations story, and, above all, a time story. The Navy is trying to shorten timelines that have historically stretched across many years. In official announcements and in defense reporting around the 2026 shipbuilding debate, the shape of that effort is becoming easier to see. The service is tying unmanned systems to a broader high-low fleet structure, linking new craft to distributed operations, and exploring modular production paths that aim to create numbers faster than traditional capital ship programs usually can. The attraction is obvious. A hybrid fleet promises a navy that is not made only of a small number of exquisite and expensive manned vessels. It suggests a force where larger warships operate alongside many smaller systems, some crewed and some uncrewed, each doing part of the work. In that picture, unmanned craft can extend surveillance, help with mine countermeasures, watch approaches, support maritime domain awareness, carry modular payloads, and operate farther forward, or in more routine roles that would otherwise consume scarce manned hulls and crews. Seen from a briefing room, that concept has a crisp logic. Seen from a pier, it becomes harder. Building a hybrid fleet fast enough means more than drafting a future force design. It means turning theory into repeatable production, reliable support, and real operational trust. It means taking systems that look promising in trials and making them ordinary enough that commanders will use them in rough weather, in crowded sea space, in alliance exercises, and in places where communications are limited or denied. That is why the newly visible procurement choices matter so much. In late May 2026, the Navy announced that 7 companies had been selected for Medium Unmanned Surface Vessel Marketplace at Sea demonstrations. The language itself was revealing. This was not presented simply as another narrow lab test. It was part of a marketplace approach, with at-sea demonstrations and a success incentive structure attached to performance that signals a desire to move faster than along conventional acquisition path, while shifting some risk toward competitive prototypes and practical results in the water. In visual terms, the difference is easy to imagine. A standard acquisition story is conference rooms, requirement binders, budget marks, and long lead diagrams. The marketplace version looks more kinetic. A support ship rides low in a gray sea. Pallets are secured on deck. Technicians in float coats move around a work area beside a control console. A crane or stern handling system guides equipment into place. Nearby, a compact unmanned vessel rocks against a launch cradle while range boats idle off the beam. In the command space, operators watch telemetry, track headings, and wait for a system to prove itself in real conditions rather than on paper. That kind of proof matters because the Navy is not trying to buy a novelty. It is trying to buy time. If the service believes it needs meaningful unmanned capacity within the next several years, then every design choice is forced into a harder question. Can this be built at scale? Can it be sustained? Can sailors learn it without a separate support empire growing behind it? Can allies work with it? Can it function when the network is strained, delayed, or degraded? The organizational signals suggest the Navy understands at least part of that challenge. In April 2026, Unmanned Surface Vessel Squadron 7 was established, with an explicit mission space connected to robotic autonomous systems operating in bandwidth, limited or denied environments. That is a sober detail. It implies that the fleet is not planning around a fantasy of perfect connectivity. It is planning, or at least beginning to organize, around the reality that future naval operations may involve interrupted links, contested networks, and long stretches where remote systems must remain useful without constant supervision. That single point matters more than many glossy presentations. A hybrid fleet cannot depend on ideal conditions. If unmanned systems only shine when every link is clean and every data path is open, then they do not solve the Navy's hardest operating problems. They become fair-weather supplements. But if they can still contribute in denied or limited environments, even in reduced ways, then they begin to look less like fragile add-ons and more like actual fleet instruments. Visualize that in a DVIDS-style sequence. Inside a shipboard control room, the lighting is dim and practical. Headsets rest against console frames. A plot flickers on one display while another screen carries camera imagery from a low, unmanned craft riding through cold chop. A petty officer marks a note on a kneeboard. Another watches a communication status page, calm but intent, while the watch supervisor glances between the sea picture and the deck log. Outside, spray runs over the unmanned vessel's bow as it keeps station in a hard gray swell. Nothing about the scene looks futuristic in the theatrical sense. It looks like ordinary naval work, which is precisely the point. Exercises also show where the concept is being pushed. In May 2026, the Navy highlighted unmanned surface and undersea systems during Arctic Century with Norway, tying them to mine countermeasures, maritime domain awareness, and undersea infrastructure protection. That is significant because the High North is an unforgiving proving ground. It imposes the kinds of conditions that expose whether systems are operational tools or presentation pieces. Cold water, shifting weather, long distance, and alliance coordination all test the practical value of unmanned systems in ways that a controlled demonstration cannot fully replicate. A hybrid fleet that is meant to matter in the real world has to show up in precisely those contexts, not only in warm water events or scripted showcases, but in coalition settings where timing, trust, and interoperability count. The Norwegian exercise suggests the Navy is trying to do that. And beyond the Arctic, the scale of coalition operations remains part of the larger picture. RIMPAC 2026, according to official Pacific Fleet framing, will gather 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. That kind of multinational exercise does not automatically validate unmanned fleet architecture, but it does remind us what hybrid integration actually has to fit into. The future fleet will not operate in isolation. It will have to function in dense combined environments, alongside many platforms, many command relationships, and many expectations. So can America build such a fleet fast enough? The honest answer is that speed depends on 3 separate races happening at once. The first race is production. The Navy appears to be searching for ways to avoid waiting decades for every increment of capability. Defense reporting around the Medium Unmanned Surface Vessel prototypes describes requirements tied to meaningful range, useful speed, survivability in moderate sea conditions, and substantial payload space, including containerized payload concepts. Those are not trivial attributes. They point towards systems that are intended to do more than hover near shore or serve as throwaway experiments. But the moment requirements become real, industrial pressure follows. Hulls have to be built, components have to be sourced, payload interfaces have to be standardized well enough to matter. Builders have to deliver not one impressive vessel, but repeated outputs with acceptable quality and supportability. The second race is fleet integration. A vessel can exist without truly belonging to the fleet. Building fast enough means not just producing hulls, but teaching the Navy where they fit, who controls them, how they are tasked, how they are sustained, and what commanders should realistically expect from them. The establishment of an unmanned squadron matters here because institutions often move slower than prototypes. The squadron is a sign that the Navy is building an operating home for these systems, not merely collecting demonstrations. But building organizations is itself a form of shipbuilding. It takes doctrine, watch-standing habits, maintenance rhythms, and a culture that knows when to trust a machine and when not to. The third race is credibility. A hybrid fleet must convince sailors, commanders, allies, and budget decision-makers that it can provide dependable contribution rather than intermittent promise. Senior leadership language about a future hedge force and risk-worthy mass shows the conceptual direction. The logic is that numbers, distribution, and robotic systems can provide options that an all-exquisite fleet cannot. But credibility is earned by repetition. A craft must launch, recover, survive sea state, carry its payload, maintain its link when it can, continue sensibly when it cannot, and come back ready to do it again. It must do this often enough that the fleet stops treating it as an exception. This is where the industrial base becomes the decisive background character. Defense analysis of the 2026 shipbuilding debate has stressed that unmanned systems are being discussed as part of a modular and distributed production strategy while also pointing to bottlenecks. That is the crucial tension. Everyone wants speed. Bottlenecks do not care. They appear in fabrication capacity, supply chains, software integration, testing availability, trained maintainers, peer support, and funding continuity. A hybrid fleet can be slowed by glamorous problems, but it is more often slowed by ordinary ones. Missing parts, delayed interfaces, competing priorities, too few operators with enough repetitions under real conditions. The camera language for that reality is not combat footage, it is logistics motion. Forklifts moving, containers along a wet quay at first light, sailors ratcheting down gear before transit, a workboat nosing alongside a pier while technicians steady a palletized module, cables coiled on non-skid, a mechanic opening a panel in a sheltered deck bay, a chief conferring with civilians over a checklist. In the background, the sea is never fully still, and the schedule never fully clean. This is how fleet architecture becomes either real or delayed. The encouraging sign for the Navy is that its current approach appears to recognize that unmanned systems cannot remain detached from the rest of naval practice. They are being tested in exercises, organized in squadrons, discussed in relation to broader fleet design, and pursued through a more competitive procurement lane. That combination suggests urgency with some institutional grounding. The warning sign is that urgency alone does not compress every timeline equally. It may be possible to select companies quickly, run at sea demonstrations, and define prototype expectations. It is harder to ensure that the industrial base, fleet support structure, and operating culture all accelerate together. A hybrid fleet only arrives when all three move at once. So the better question may not be whether America can build unmanned vessels fast. It can almost certainly build some of them fast. The harder question is whether it can build enough trustworthy hybrid capacity fast enough that the fleet begins to change before the strategic window changes around it. That remains the gamble, not a gamble on whether robots can float, navigate, or transmit. A gamble on whether procurement, industry, doctrine, and seamanship can converge in time. If they do, the Navy gets something more durable than a trend. It gets additional mass, additional reach, and additional flexibility in waters where distance and uncertainty punish delay. If they do not, the United States may still possess impressive unmanned demonstrations, but not yet the hybrid fleet it has been describing. And in naval terms, that is the distinction that matters. The ocean does not reward ambition by itself. It rewards systems that arrive, endure, and contribute when the weather turns and the distances open. In the Pacific, the test of this idea will not happen on a slide or in a budget hearing. It will happen in company with allies, across long distances, inside a tactical picture that is always incomplete and never still. That is why exercises such as RIMPAT matter so much to the Navy's unmanned future. They place new systems inside the one environment that really counts, a coalition fleet at sea, with many commanders, many platforms, and many competing demands for time, bandwidth, and trust. RIMPAC 2026 is the right scale for that question. The U.S. Pacific Fleet announced it as the 30th iteration of the exercise, bringing together 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. Those numbers matter because they describe more than a naval gathering. They describe a crowded military ecosystem. In that kind of environment, every new system has to prove it can contribute without creating confusion, delay, or a new burden for the crews already managing a complex operation. On screen, this is where the imagery can become very concrete. A gray morning over the Pacific. A formation of ships spread across a moderate sea state, white spray lifting from the bow. Flight deck crews in colored jerseys move with practiced economy beneath the turning helicopter rotor. Inside a combat information center, operators study layered displays under low light, tracking air, surface, and subsurface contacts as watch teams rotate through their stations. Far below that visible choreography is the harder question: can manned ships, aircraft, and unmanned systems all share the same operational rhythm without slowing the fleet down? The Navy clearly wants the answer to become yes. Its own messaging around major exercises emphasizes interoperability, missile proficiency, anti-submarine warfare, and mine clearance. Those are not abstract categories. They are some of the most demanding tasks in naval operations, and they depend on coordination more than novelty. A fleet can be technologically impressive and still fail if its data arrives late. Its operators cannot trust its outputs, or its logistics chain cannot keep the force supplied and synchronized. That is why unmanned systems become more interesting in allied exercises than in isolated demonstrations. In a controlled event, a robotic craft can perform its assigned function and still leave the larger force unchanged. In a multinational exercise, the same craft has to fit into briefing cycles, command relationships, safety protocols, launch and recovery windows, and the everyday friction of working across different navies. It has to be seen not just as a machine that works, but as a participant in a fleet that works. The Navy already has one sign that it understands this distinction. In April 2026, Unmanned Surface Vessel Squadron 7 was established with an explicit focus on robotic autonomous systems operating in bandwidth-limited or denied environments. That detail is more revealing than it may first appear. It suggests the Navy is not designing its unmanned future around perfect connectivity. It is designing around the expectation that communications will be contested, incomplete, or interrupted. In a coalition fight, that assumption is not pessimism. It is realism. Visually, that realism can be shown without entering sensitive territory. A small, unmanned craft rocks alongside a support ship during launch preparations. Sailors in flotation gear secure lines and check fittings on a working deck slick with spray. Antennas turn above the superstructure. In a planning room, officers from different partner nations point across charts and screens discussing sectors, timing, and deconfliction. A camera lingers on hands moving through checklists, then cuts to the wake of a vessel heading into open water. The point is not secrecy or spectacle. The point is process. If the Navy hopes unmanned systems will become part of a future battle network, that network has to survive the realities of allied operations. Different fleets bring different equipment, different training pipelines, and different command cultures. Even when partners are close and experienced, interoperability is built through repetition rather than assumption. RIMPAC offers a setting where the Navy can place new concepts under precisely that kind of pressure. There is already evidence that this effort extends beyond the warm waters of the Pacific. In May 2026, the Navy described unmanned surface and undersea operations during Arctic Sentry 2026 with Norway. The listed mission areas included mine countermeasures, undersea infrastructure protection, and maritime domain awareness. That combination is important. It shows unmanned systems being associated not with a single mission, but with a family of difficult maritime problems shared by allies operating in sensitive waters. The high north and the Pacific are not the same theater, but the lesson is similar. If unmanned systems are going to matter, they must support persistent observation, extend presence, and help crews cover more water without simply adding exhaustion to already stretched forces. They must also function in partnership with allied navies that have their own responsibilities, geography, and operational habits. The future battle network, if it arrives, will not be purely American in its daily workings. It will be multinational, uneven, and constantly negotiated in practice. That makes the Allied dimension more than a diplomatic accessory. It is part of the system design problem. A vessel that performs well technically, but cannot integrate smoothly with a coalition force, is not solving the real strategic challenge. The Navy's unmanned ambitions point toward a distributed maritime picture, in which many nodes contribute to a broader awareness and a wider set of options. But a network is only as strong as the relationships, procedures, and trust that bind those nodes together. This is where the Navy's larger thinking begins to come into view. Defense reporting in 2026 described a future force shaped by what senior leadership called a hedge against uncertainty. One built around robotic autonomous systems and what was described as risk-worthy mass. The phrase matters because it captures a change in naval logic. Instead of relying only on a smaller number of exquisite platforms, the Navy is exploring a force that includes more numerous systems able to absorb risk, extend reach, and complicate an adversary's calculations. In calm briefing language, that sounds rational and measured. At sea, it becomes a harder proposition. Risk-worthy mass still requires maintenance, transport, launch procedures, operators, spare parts, software support, and clear tactical roles. It requires commanders to know when to trust a machine and when to discount it. It requires allies to understand what a given unmanned contact is doing in shared waters and how it fits the operation. None of that arrives automatically with a prototype. A DVD-style sequence here can stay grounded in ordinary naval labor. Forklifts shift palletized stores across a replenishment deck. Sailors strap down equipment as the ship rolls. A small work center checks connectors, housings, and mission gear. In a control room, an operator monitors system health while another tracks the broader picture. Above them, the bridge team watches sea and traffic through salt-streaked glass. This is the true environment of a future battle network, not just sensors and code, but movement, fatigue, weather, and the discipline of crews making machinery useful. The industrial question sits behind all of it. Defense analysis of the 2026 shipbuilding debate linked unmanned systems to a broader high-low fleet mix and to modular approaches meant to widen production options. That matters because the Navy's unmanned push is not just about tactics. It is also a response to time. Traditional shipbuilding remains slow, expensive, and constrained by industrial bottlenecks. Unmanned programs are being discussed as one way to add capacity and flexibility without waiting decades for every answer to arrive in the hull of a major combatant. Reporting in 2026 also described plans for large numbers of smaller unmanned surface vessels in the Indo-Pacific by 2030, alongside a force of medium unmanned surface vessels and containerized payload ideas. Even treated cautiously, as reporting rather than settled fact, the scale of that ambition is unmistakable. The Navy is not talking only about occasional robotic escorts or isolated specialty craft. It is talking about architecture, a different pattern of presence, sensing, and distributed capability across a vast maritime theater. And that brings the story back to RIMPAC and to allies, because if architecture is the goal, exercises are where pieces first learn whether they can actually live together. A future battle network is not simply hardware linked by data links. It is a set of habits, expectations, and tested relationships. It has to prove that a destroyer captain, an aviation detachment, an allied staff officer, and an unmanned systems team can all act from the same picture without paralysis. It has to prove that logistics can support dispersion. It has to prove that information can remain useful even when bandwidth is constrained. The establishment of a dedicated unmanned surface vessel squadron points to the Navy's recognition that this will require its own operators, doctrine, and organizational attention. The Allied exercises point to a recognition that this future cannot be built inside a single service culture alone. And the procurement experiments around medium unmanned surface vessels point to a recognition that speed now matters almost as much as elegance. So Chapter 8 is not really about whether allies will join a fashionable American technology trend. It is about whether the Navy can make unmanned systems legible and useful inside Allied maritime operations before the strategic window narrows further. If it can, then exercises such as RIMPAC become more than rehearsals. They become workshops for a new fleet design. If it cannot, then the vision of a hybrid fleet remains vulnerable to the oldest naval verdict of all, promising in theory, but too fragile in practice. From the deck edge, from the watch floor, from the small control station where an operator studies a narrow stream of data while the ocean keeps moving beyond the hull, the issue becomes very simple. The future battle network will not be judged by how confidently it is described. It will be judged by whether Allied fleets can carry it to sea, keep it coherent under pressure, and make it matter when distance, weather, and uncertainty begin to strip away every comforting assumption. What comes after the ship may matter as much as the ship itself. For more than a century, naval power has been easy to picture. It has had a hull, a silhouette, a bridge, a wake, and a commanding officer standing somewhere within a chain of steel compartments that could be touched, inspected, and understood. Even when fleets changed their sensors, missiles, propulsion, or aviation, the basic image remained familiar. A navy was still something you could count at the pier and follow across the horizon. What is emerging now is harder to summarize in a single frame. It is still a fleet, still shaped by distance, weather, endurance, logistics, and command. But it is also becoming a wider system of manned ships, robotic autonomous systems, containerized payloads, command links, and industrial decisions that reach well beyond any one deck. That is why this story is not really about whether a single medium unmanned surface vessel succeeds or fails in isolation. It is about what kind of fleet the Navy believes it will need when the old certainties of scale and production no longer feel sufficient on their own. Official announcements in recent months have made clear that this is moving beyond a laboratory discussion. The Navy has selected 7 companies for marketplace at-sea demonstrations tied to the medium unmanned surface vessel effort, and it has paired that selection with a success incentive instead of relying only on the slowest features of a traditional acquisition sequence. That does not guarantee a result. It does show intent. The service is trying to shift risk, compress time, and learn at sea rather than waiting for a perfect answer on paper. In visual terms, the closing image is not a futuristic armada racing in formation. It is something more procedural and in some ways more revealing. A gray ship holds steady in a moderate sea. The flight deck is wet with spray. Line handlers move with practiced caution. A small crew works at a console under red and white task lighting. A crane or boat handling system swings through a controlled arc. A compartment screen glows with tracks and route lines. A rigid hull boat cuts across the wake. On another day, under another sky, a vessel with fewer people aboard, or none visible at all, moves through the same operational picture. Around it, the ordinary business of the fleet continues: checklists, radios, fuel planning, maintenance rounds, watch turnover, stores moving by pallet, and operators watching for the small deviations that become large problems at sea. That is the real setting for the Navy's gamble. Not a clean concept slide, but the crowded routine of maritime operations. If unmanned systems are going to matter, they will have to fit into that world. They will have to hold relevance in bandwidth-limited or denied environments, the exact condition highlighted with the establishment of Unmanned Surface Vessel Squadron 7. That detail matters because it pulls the discussion away from the most comfortable assumptions. A robotic vessel that works only with perfect connectivity is not much comfort in a contested theater. A system that contributes when links are degraded, distances are long, and the tactical picture is incomplete begins to look more like something a fleet can actually use. That question becomes even sharper when the frame widens beyond a single service. In the high north, the Navy recently operated unmanned systems during a bilateral exercise with Norway, in a context that included mine countermeasures, maritime domain awareness, and the protection of undersea infrastructure. Those are practical missions, not science fiction. They point to an uncomfortable truth that conventional navies have always known. The sea is too large, too cold, too complex, and too changeable to be watched by a handful of exquisite assets alone. Alliance operations make that clearer, not simpler. Different procedures, different communications habits, different ships, and different priorities all meet inside the same water space. If unmanned systems are going to earn their place, they must do more than move. They must help Allied fleets see, sort, clear, protect, and coordinate. That is why the Pacific remains the proving ground in everyone's mind, even when the demonstrations happen elsewhere. BRIMPAC 2026 brings together 31 nations, 40 surface ships, 5 submarines, and more than 140 aircraft. Numbers like that matter because they remind us what scale really looks like in naval terms. A fleet architecture is not validated by a press event. It is validated when it enters a multinational exercise environment where every unit competes for space, bandwidth, fuel, attention, and command clarity. In that setting, an unmanned vessel is not impressive because it exists. It is useful only if it can become part of an Allied operational rhythm without adding more confusion than value. And this is where the phrase, "after the ship," begins to mean something more specific. It means the fleet after the age in which presence was measured mostly by crude hulls alone. It means a force in which mass may come not just from building more major combatants, but from pairing those capital ships with many smaller systems and a smaller number of medium unmanned vessels that can extend sensing, complicate targeting, and carry modular capability into the battle space. Defense Analysis Reporting has described a Navy interest in deploying thousands of smaller unmanned surface vessels in the Indo-Pacific by 2030, alongside more than 30 medium unmanned surface vessels. Those figures are not official guarantees of what will exist on that date, but they do help explain the scale of ambition behind the current effort. This is not a side project. It is a bid to change the geometry of naval presence. The logic behind that ambition is easy to understand, even if the path is not. Traditional shipbuilding remains slow, expensive, and constrained by industrial bottlenecks. At the same time, Navy leadership and naval reporting have increasingly framed the future fleet as a high-low mix, supported by unmanned systems from seabed to space and by a more modular approach to production. That broader context matters. The Medium Unmanned Surface Vessel is not just a new craft to be evaluated on its own lines. It sits inside a larger debate about what can be built fast enough, in enough quantity, and with enough flexibility to matter before the strategic environment moves on again. In a documentary closing sequence, the imagery almost writes itself because the tension is already there in the routine. A camera holds on boots crossing a non-skid deck as the ship rolls gently. A control station shows a coastline receding into low haze. Sailors and cranials and float coats move around secured equipment. A replenishment evolution begins somewhere else in the formation. Fuel hoses and pallets reminding us that endurance is always paid for in movement and material. In a command space, officers and enlisted watchstanders lean toward displays, not dramatizing anything, just maintaining the picture. Outside, the sea state is manageable but not decorative. There is always wind noise, always corrosion, always some small mechanical issue waiting for attention. Any future robotic fleet still has to survive this texture of reality. That may be the most useful correction to both the hype and the skepticism. The hype imagines unmanned systems as a simple replacement for the burdens of manned naval power. The skepticism imagines them as toys that disappear at the first sign of weather, friction, or adversary pressure. The more serious view is harder and less theatrical. The fleet after the ship is still a fleet of burdens. It still has to move fuel, parts, software updates, payloads, operators, maintainers, and tactical understanding across long distances. It still has to work with allies. It still has to function when plans go stale. What changes is not the disappearance of naval complexity, but the effort to distribute it differently. That is why the current medium unmanned surface vessel requirements, as reported in defense analysis, are so revealing. A vessel designed around meaningful range, useful speed, operation in sea state 4, and a substantial payload begins to sound less like a novelty and more like an operational compromise. Not a replacement destroyer, not an empty publicity device. Something in between, a platform intended to carry modular function across real water under real constraints. Again, those figures are part of reported prototype requirements, not the final verdict of a fielded class. But they show the Navy is not merely chasing the smallest and easiest drone. It is searching for a vessel that can live in the awkward middle ground, where logistics, payload, survivability, and affordability all press against one another. The larger doctrinal language points in the same direction. Senior Navy leadership has described a future hedge force shaped by robotic, autonomous systems and risk-worthy mass, rather than a one-size-fits-all fleet design. That phrase, risk-worthy mass, captures the entire strategic wager. It suggests a force that can absorb uncertainty better because it is more distributed, more numerous in key layers, and less dependent on every mission being carried by a small number of highly prized hulls. But words like that are still only words until they pass through commands, squadrons, shipyards, and exercises. Institutions do not change because a concept is elegant. They change because enough people begin to operate, supply, and train around the concept until it becomes habit. So the ending here is not triumph and it is not dismissal. It is recognition. The Navy is placing a serious bet on what the fleet can become after the ship stops being the only central object in the picture. Not after the ship disappears, because it will not. Carriers, destroyers, submarines, logistics, ships, and allied surface combatants remain the framework within which all of this must function. But after the ship loses its monopoly over how presence, mass, and tactical effect are generated, in that future, a formation may still be led by familiar silhouettes on the horizon, while much of its reach is carried by smaller, quieter, harder to summarize systems moving ahead, beside, below, or between them. And in the end, the sea will judge the idea the way it judges everything else, not by briefing language, not by procurement optimism, not by how modern the diagrams look. It will judge by whether these systems can be launched, recovered, sustained, directed, trusted, and adapted in the company of real fleets. It will judge by whether Allied sailors and commanders find them useful when the picture is crowded and the weather turns. It will judge by whether logistics can keep pace with concept. It will judge by whether industry can produce enough of the right things in time. It will judge by whether a Navy trying to build a high-low mix can turn experimentation into structure without losing coherence along the way. For now, the final image is a modest one. A horizon line, a working deck, a watch team on station, equipment secured against motion. A gray ship continuing on course, while a new set of tools begins to find its place around it. That is the fleet after the ship. Not a fleet without sailors, and not a fleet without ships. A fleet still shaped by steel, weather, distance, and discipline, but increasingly extended by systems designed to carry some part of a burden farther forward. Whether that gamble succeeds is still unresolved. But the gamble is no longer abstract. It is at sea.